I'm here with Alan Mackworth, who received the 2019 Association for Constraint Programming Research Excellence Award. And I'm here to interview Alan. I'm Gene Freuder. Alan and I have known each other for a long time. I think, Alan, we first met in 1975 at a Canadian AI workshop.
Yeah, I think that's right. In fact, we were both talking about constraints. I actually knew your work earlier. I knew you were working on hammers, understanding pictures of hammers. So,
Right.
but it was good to meet you, and that's been the start of a very long friendship. And we've occasionally collaborated on some really nice pieces of work.
Indeed. The But let's go back to the beginning. How did you first become interested in computers?
Well, you see, going back quite a long way, I remember going to the Festival of Britain. We lived in Cambridge, in England at the time. And we went to the Festival of Britain, which was to celebrate Britain coming out of World War II and so on. And they were demonstrating Britain's advances in computers. I mean, Alan Turing and all of that, right? And they had a machine there that could actually play noughts and crosses, as we call it there, tic-tac-toe in American. Um, and it was amazing to me that a mechanism could make decisions and actually play a game like that. And of course, it always beat me as a 5-year-old. I wasn't very good at tic-tac-toe, but I was just fascinated by the prospect, and maybe that planted a seed. Um, I certainly, I read a lot of science fiction as a kid, and I tried to build robots out of old record players, things like that. Um, had good fun playing around with various mechanisms, but it really started when I got to university. I went to the U of T, University of Toronto in 1962, and I was doing engineering physics. We had a small IBM machine there, but most of my work was done in the summer. Computer science really didn't exist in the universities in those days, in 1962. But I got a job with a company called Ferranti Electronics, which were building one of the world's first time-shared computers. And they had to build the operating system and the compilers and so on. And I worked with them on that, but also did a lot of work on programming stochastic simulations of communications channels. So it was a great education in computer science before computer science really existed in the university.
So you built robots out of record players.
I tried to.
How did that work? You took them
Well,
apart.
these
You
were
took your
mechanical.
grandfather's record player apart, and
Well, I found some junked old record players, and they had, electric motors which drove the turntable. So I was able to salvage electric turntables, and they had, belt drive, I think it was, and I tried to connect that up to a pair of wheels and so on. I was about 10 when I was doing this. That didn't go very far. I think my most successful robot was built out of uh, a wooden cotton spool. We used to get cotton on wooden spools, and you could cut notches in them and put a rubber band through it and attach a match to the end unlit and wind up the rubber band, and it would actually move across the landscape, a little bit like Simon's ant moving across the beach, right?
that's interesting, given your future involvement in RoboCup, which we'll get to later. And the tic-tac-toe is interesting. Given that you ended up working on constraints, an early version of Sudoku might have been more appropriate. But how did you eventually get interested in constraints?
Well, let me see, after a spell at Harvard where you and I probably overlapped but didn't run into each other,
Yeah.
I went back to Toronto to teach control theory. So in teaching control theory, I started to understand the issues of homeostasis, how a biological system maintains its state despite environmental changes. And, more technically, control theory like PID control and so on, how you maintain a constraint dynamically against varying environmental conditions. That was one view of constraints. And then as I started to get more interested in AI, I encountered RefRF. Rich Fikes built this system for problem solving using constraints. And he had a form of constraint propagation in there, which kind of intrigued me. It wasn't formalized, but it worked well. And then at Sussex, where I did my PhD with Max Clues, my first job with Max was to implement his clues labeling, which became known as Huffman clues labeling because they discovered it independently for labeling line drawings of polyhedral scenes. And, there are the constraints is that if you're labeling a corner with one of the corner labels, then the edge between those two corners has to have the same label, obviously, so but we solved it using backtracking, which was very expensive and very slow for large scenes. But then Dave Waltz extended the Huffman clues labeling to include shadows, but also developed this propagation algorithm so that you could effectively prune the set of constraints quickly before you did any depth-first search. In fact, you can intersperse that with the depth-first search. And that was fascinating. I remember seeing Dave Waltz's animation that I think Pat Winston showed it. And that intrigued me. And then in my thesis, I worked on constraints in vision, looking not just at constraints on edges and corners, but actually on surfaces, looking at the surface gradients to see how, if you have two surfaces intersecting in 3D space, then the gradient of one surface constrains the gradient of the other surface through that edge. And I used that to build a program which interpreted line drawings of polyhedral scenes, but took account of surface orientations and allowed for detection of impossible objects and so on, which previous systems couldn't do.
So I think a lot of the early work on constraints had a connection with computer vision. The um, there's now deep learning, that sort of thing seems to have taken over. The Do you think there's still a role to play for symbolic processing in computer vision?
Yeah, I mean, despite Jeff Hinton, I think symbols do exist. I think we need symbols in our AI systems. And I think the higher levels of computer vision will need things like ontologies and constraints between interpretations and so on. But that remains to be seen if it's absolutely necessary. And I think I should say a little bit more about the paper we developed. I guess I developed on consistency in networks of relations, which, we won the AIJ Classic Paper Award in 1977. The paper was in 1977. We won the award later. But that was, in a way, you could abstract the Waltz filtering algorithm away from vision to apply to constraints in general. And it built on some work by Ugo Montanari, who developed basically what I call path consistency. But earlier than that, we developed arc consistency, which is a generalization of Waltz, developed several algorithms for that and various path consistency algorithms. So these algorithms can be used to radically prune the search space in many cases for a CSP, and they can interleave these techniques, these filtering algorithms with exhaustive search.
You had an outstanding student around that time, Raymond Seidel, who had a role in bringing us together, but who sadly passed away quite young. Do you want to say a few words about Raymond?
Yeah, Raymond was a brilliant student. He was in my graduate course learning about constraints, and he went on to develop a dynamic programming approach to constraint satisfaction, which he published independently. And in the course of that, I suggested, since I knew you'd be interested, that he talk to you. So he talked to you, and you had a conversation apparently. And in fact, I had told him that I developed a proof, the Waltz filtering seemed to have this interesting sort of linear behavior. Um, and the question was, is that always the case, or is it just an accident of the particular examples that he chose? So the conjecture was that the time complexity of arc consistency is linear in the number of constraints. And I'd actually developed a proof to that effect. So when Raymond talked to you, turned out you'd also got a proof for the same hypothesis. And so that was exciting. So we talked and we collaborated and produced a joint paper which went beyond arc consistency to look at complexity of path consistency and so on.
Yes, that was I think a very good example of how people can collaborate rather than just compete all the time. And that did lead to that paper, which in turn led later on, because the paper was honored in a way that resulted in an opportunity for us to write a little follow-on paper on revisiting the that original paper for another issue of the AI Journal. So I wondered if you have any other thoughts about revisiting that paper.
Well, I mean, first of all, it was just very satisfying to find an analytic proof for the linear conjecture based on Dave Waltz's experimental data. Um, but of course, it's really nice to have a theoretical guarantee. And it meant that, you could essentially work on larger problems using these techniques. And there's always a question of whether is our consistency enough combined with search, or do you want to go to path consistency or higher order K consistency as you worked on and so on. And there's some really interesting trade-offs to explore there.
So another way that we collaborated is we co-edited a special issue of the AI Journal on constraints, and uh, in that issue or volume, you had a paper yourself on the logic of constraint satisfaction, in which you viewed constraint satisfaction within a space of logical reasoning and representation systems. Do you want to tell us something about that?
Sure. I mean, the first thing is obviously to point out that SAT, satisfiability of clauses in propositional logic is a CSP itself. Okay, it's a very simple form of CSP. And there's a huge amount of effort being put into building SAT solvers, both deterministic and non-deterministic SAT solvers, because it has a very important applications in verifying hardware and so on. Probably more work than has been put into CSP solvers. So maybe you could exploit that effort by translating CSPs to SAT versions. And there are various ways to do that. And I looked at various options and various pros and cons. Typically, when you do that, you'll get a very large blow up in the size of the problem. It'll explode exponentially because you have to put in all sorts of no goods and so on. But maybe because of the efficiency of SAT solvers, it may have well been worth it. And that was worth exploring. The theoretical point I made was that arc consistency in CSP can be seen as isomorphic to a form of hyper-resolution in SAT.
You ultimately took a particular approach to constraints with your paradigm of constraint-based agents. And can you tell us something about that paradigm?
Sure. Yeah, I mean, this is sort of a different take on constraints. Mostly, in the CSP community, you think of these as static constraints. Time isn't mentioned, although CSPs obviously have been used to, Alan's work on temporal reasoning using the CSP approach, but the constraints typically don't change over time, whereas in the world, that's not true, right? So solving, Sudoku problem is not the same as trying to kick a soccer ball, just to take a random, non-random example. So inspired by robotics, this was really work with Ying Zhang, one of my best PhD students. We wanted to develop a theory for AI that was about embedded and embodied agents with emergent behaviors, inspired partly by Rod Brooks's work. Rod's work was quite experimental, but his various architectures were convincing arguments that robots had to be built essentially from the bottom up, modeling evolution. But we were also interested in more formal properties, like being able to prove safety and correctness of robot controllers, which could, if you could do that, that could lead to support for work in robot ethics and so on. Because a lot of work in robot ethics we thought was quite naive, because it assumes that we can state properties of robots and prove them, which we couldn't do at the time. Still can't do for most robots, but we're improving a little bit. So there, obviously, the constraints are dynamic. If you're trying to catch a moving ball, then you're trying to reduce the distance between your hand and the ball, but the ball is moving as you're trying to catch it. So as you're trying to, if the ball were fixed in space, that's fairly easy. You just use a PID controller and reduce the distance, and you solved it. But if the ball is moving, then you have to maybe develop a theory of how the ball is moving, predict where it'll be, and so you can actually intersect it in the future at the same space and time. So that's a very different view of constraints than the CSP view. So built on that idea, we essentially said that a constraint-based agent is one where you model an agent as a controller talking to a body, and the body talks to the environment. All of those are modeled in the same language. We call it constraint nets. And then you can, if you know properties of the environment and properties of the body, then you can construct a controller, and the controller may well be a constraint solver. It may be using gradient descent, something like that, to reduce the error on the constraint to zero. But this idea of using constraints as dynamic and controllers as constraints solvers allows you then to nest controllers the way that Rod Brooks's subsumption architecture does. We can build controllers for simple constraints and then build controller on top of that that talks to the controller below, and so on. You build the robot controller as a hierarchy of controllers. That's a basic idea.
So it's intrigued by your mention of robot ethics. So, of course, now with the explosion of interest in AI, there's a lot of concern about safety and ethics and all that sort of thing. That you were thinking about that quite some time ago.
Yeah, I mean, we wrote a paper on using constraint-based agents as an approach to robot ethics a long time ago. I think it has stirred some interest. I do see a huge resurgence of that work, because now, with self-driving cars and so on and so forth, we need to be able to prove properties. You're not going to get certification for a self-driving car unless you can prove certain properties of it. Now, maybe you can, do extensive millions of experiments, but there'll always be corner cases. Of course, you'll never have a perfect car, But just as, for automatic braking systems, you can prove that under certain conditions, they will always work correctly, assuming the hardware works correctly. We should be able to extend that kind of theory to higher levels in the autonomous car hierarchy.
Yes, you don't want a demolition derby.
Right.
So there's a great story that I heard Pascal tell in an interview that was done with him about a eureka moment that he had reading one of your papers. And uh, he said there was a footnote proposing that it would be advantageous to take these AI constraint satisfaction techniques and put them in a programming language. And he was like, wow, that's what I need to do. And the rest is history. Did you have any eureka moments that you can recall that, or is this a particularly interesting, or is there a particularly interesting story behind any of your discoveries?
Well, first of all, I mean, it is a great story. It's not quite true because it wasn't a footnote. Pascal got it slightly wrong. I mean, yeah, it was really exciting to me that Pascal found that note because I sort of put in, there was a whole section in the 1977 paper, consistency paper, not just a footnote. It actually was section 9.4. It was titled AI Programming Languages. And it actually had suggested indeed what Pascal said, to embed constraint satisfaction techniques into language interpreters. And I actually gave an example of I didn't implement it, but I proposed implementing in microplanner, which was Carl Hewitt and Jerry Sussman, Terry Wintergrad's language, subset of Hewitt's planner. But microplanner is basically just a subset of Prolog, not quite as elegant. But I proposed, there would be really substantial advantages, even just retrieving from a database of assertions. You could do it much more efficiently if you use these consistency techniques. And Pascal did it. He did an amazing job in Prolog. Constraint handling in Prolog was the way, what he called his language chip. It was a tour de force. And it led, of course, to almost all the other constraint programming languages that came after. But in terms of eureka moments for me, I mean, actually, that was a eureka moment. That idea that you could put it in programming languages, these techniques could be more generalized into programming languages, not just for CSPs, was a eureka moment for me. And I was delighted that Pascal picked up on it because I wasn't working on extending it. I remember talking to him about 6 months after he had that eureka feeling. And I said, go for it. I'd just love to see it happen. And he did it beautifully. And I guess the network consistency work, our consistency, path consistency, bringing together a whole bunch of different experimental approaches and some other theoretical work into one uniform framework, that was a good feeling.
So another possible eureka moment, you've been called the father of the RoboCup. And I think you said that was in some sense a eureka moment, realizing that you could build fully autonomous, small, self-driving cars back in 1991.
Yeah, so and you might ask, what's the connection with constraint programming? I mean, I really see myself more as an AI person than a CP person. I've had some influence in CP, I guess. Yeah, what I really wanted to do was to force AI out of the narrow concern with puzzles and logic and so on, and more generally the so-called go-fair approach, good old-fashioned AI, like added robotics, good old-fashioned AI and robotics paradigm, which makes certain assumptions about the way the world is. There's only single agent, and you can predict the effect of your own actions perfectly, and in order to do strips like planning and so on and so forth. But also it has certain assumptions about how you build intelligent systems, namely that you have a perception box, you have a reasoning box, and you have an action box. and they're connected by fairly narrow channels. Uh, I think now we realize that's wrong, with deep learning and so on. We have end-to-end systems. But then that was the standard approach, and people either saw themselves as working in perception or reasoning or in robotics. But uh, by coming up with a problem like playing soccer, it's like, how would you build an intelligent system to play soccer and collaborate with other soccer players and to compete with soccer players and so on, dealing with the ball and variable conditions? That's a real challenge. And I realized, I guess the eureka moment was we just about had the technology to be able to do this. We had some SIMD, fast parallel computers for sensor image processing. We had one MIP processors, very slow by today's standards, but we could just about do some parallel processing on the planning side, and then we could close the loop. And we did it by using radio controlled cars rather than putting any smarts on the robot. We had offboard smarts, but they were still fully autonomous. So we were tracking the cars using overhead cameras. We could extract blobs from the image at almost video rates and send control signals back to each car separately, each making their own decisions. And we were able to get one-on-one soccer going with big robot trucks, and then we used small cars steering. You get to steer the car, so that's a huge. They're non-holonomic robots. In other words, you can't turn in place. You have to back and fill, do a 3-point turn to turn around. That's a hard planning problem. But we were able to get it going with one-on-one and then two-on-two cars, and we developed controllers using some constraint ideas on top of that. But this took off. We started in 91. I guess we had it all working by 93. And then, inspired various Japanese researchers who came through our lab, say, hey, this is exciting. Katano-san was one of the first to propose RoboCop, the tournament, and we participated in the first tournament, 95, et cetera. And it's become a huge thing ever since. And it is a huge connection for many students. That's their first exposure to AI and robotics, is to build a RoboCop team, either in simulation or in the small league, the middle league, the big league, humanoid robots, et cetera. It's really exciting. But the connection to constraint programming is that we use soccer as a domain to test our constraint-based agent theories, which are constraint-based, obviously, using dynamic constraints. It's a simple example. To score a goal, the player has to connect with the ball at the right time, at the right place, facing in the right direction, and kick the ball in that direction toward the goal. That's a very complicated constraint to solve. And you have to do it by avoiding other players at the same time, and et cetera, or deciding, should I kick a goal, or should I pass to a teammate who's in a better place to score a goal, and so on. We tried to, and we built some controllers in simulation that solved that. And we decided that the various ways of building these controllers, but they're mostly ad hoc, and they weren't very satisfying from a clean point of view.
Well, bringing together disparate areas like that might be regarded as a kind of research heuristic. Do you have any other heuristics you can share that some of our listeners might use to help them uh, in discovering and developing new research ideas?
Well, it's hard to look back and abstract that kind of perspective. But I guess one is, obviously, don't get too absorbed in your own particular research paradigm, because, you think about how AI developed sort of out of cybernetics and control theory and communication theory with Shannon and Wiener and Minsky and McCarthy, and so on. And those days were very exciting, the late 40s, early 50s. Um, and that was a huge amount of cross-fertilization between these different areas. And then AI developed as a separate area. And we said, well, we're not interested in pattern recognition or in control theory, and information theory, and so on. We're going to develop, symbolic AI. And I think that was a mistake, in retrospect, looking back at the development of the field. Um, and certainly by expunging pattern recognition from AI, as Ichkai did formally in 1973, I think it was, we wouldn't accept any pattern recognition papers. That was a huge problem. So it meant that perceptron-like work and the deep perceptrons that came later developed their own conferences and developed in isolation. So one research heuristic arising from that thinking is that keep looking around at other areas that are trying to solve similar problems. Maybe they don't have all the right ideas. Maybe they've only got part of the elephant. Maybe you've got another part of the elephant. Maybe if you come together, you could come with a better theory of elephants. So I guess for our constraint-based agent works, we're trying to put together control theory and artificial intelligence and constraint programming into one unified theory. And there is nothing more powerful than a good, clean, unified theory in terms of practical application. That's another important lesson, I think. So other possible lessons are you need to look for the right abstraction. If you have a theory or something that seems to work well in some domain, can you slightly formalize it? Maybe that when you formalized it, you lifted it a bit to apply to other domains. Don't be happy with your theory. Find the right application, or in fact, maybe prototype domain is better than application that will stretch and extend your theory. If you've got something that works on a certain problem, then what interesting extensions can you make to that problem? And always work between theory and application. Don't get trapped in pure theory. And my tendency, and not everyone is like this, of course, many people are better off just working in theoretical applications, and that's great. But my approach is always to try and build experimental prototypes. Not going all the way to products. That's not the role of a researcher, but build prototypes to test your hypotheses and then go back to your theory bench and see what you have to change.
Okay, well, you've obviously had a very successful research career yourself. But in looking back, is there anything you would change or do differently if you had the chance?
Hmm. Hmm. Good question. So maybe I should have gone to MIT rather than Harvard when I went to grad school. That's the first thing. But in retrospect, I'm happy with how that all turned out. I was very lucky that I got the opportunities I did. Somewhat random search, but it worked out really well. But yeah, in terms of the research, I think we should have emphasized uncertainty more. I had a good argument with Jeff Hinton about this. He said, you really should have emphasized probability more, and he's right, we should have. We did develop probabilistic constraint nets. We should have developed that earlier, allowed for uncertainty, both in the environment and in the decision-making. Stochasticity is important. I should have learned that lesson from my very early work. And I think if we'd done that, we would have probably been able to provide them as a more formal basis for neural networks and explainable artificial intelligence, which is a critical need these days.
So, are there any aspects of your research that you'd particularly like to see further developed? I guess maybe this probabilistic aspect is one. Is any others?
Yeah, that's certainly one. but more generally, the formal constraint-based agents paradigm. I think there's a lot more mileage in that. It's still the case, I think, that the current work is not emphasizing embodied agents that interact with their environments as the tool to real intelligence. I think that's obviously how we developed biologically through evolution. We interact with our environment. We learn through evolution. We learn through individual learning and so on. But it's through a very close coupling with the environment. And I don't see that in a lot of work currently in AI. There's a real need for that. And I think, our proposal of constraint-based agents is one way forward. It's maybe too formal for many, but again, I do think you need a good theory to make great progress.
I recall that as president of AAAI, you gave a presidential address on agents, bodies, constraints, dynamics, and evolution. Can you recap some of that for us as it relates to CP in particular?
Well, the big picture in that talk was to describe the evolution that I saw as necessary and occurring in some places of AI from GoFair, good old-fashioned AI and robotics, which is not a derogatory term. Some people, Ray Ryder was very offended when I used that term to describe his work. I think it's important, critical work. It just doesn't go far enough. We have to go to situated, embodied, and embedded agents. That is, they're situated in a world. They have a body that they interact with that world. That's how we learn. We're not disembodied whatsoever. And part of our intelligence is in our bodies, at various levels in our bodies. And it's also the intelligence arises in the interaction between the agent and the environment. It's not just in your head. And that lesson, I think, still hasn't quite been learned. Many people have been preaching it, and we have our version of it, which is our constraint-based agents paradigm. But it was really preaching, in this case, not to the choir, because I think many people are still skeptical and don't see the need for this to go this way. I think it's critical as we develop theories of intelligence. And I mean, not just for applications, but if we want to understand, I think AI has two sides to it. One is science, the science of intelligence. How can intelligence arise in mechanisms, whether they're biological mechanisms or mechanical mechanisms or electrical mechanisms, electromechanical mechanisms? How can it arise? Can we have a formal theory of that? And secondly, the engineering side of AI, where we take some of those theories and apply them to building smart systems. And again, many people aren't willing to grant us that distinction, but I do think we are scientists first and foremost, and we need to develop the science more carefully rather than just rushing to develop the latest product and hit the latest niche in the market.
So broadening out a bit, you actually have written an AI textbook you recently came out with the third edition, which you co-authored with David Poole. Give it a little plug, Artificial Intelligence, Foundations of Computational Agents, which relates to what we've just been talking about, presumably. And it, of course, includes a chapter on reasoning with constraints. So more generally, what are your thoughts about the teaching of constraint programming?
Right. So let me say just a little bit more about the book.
Oh, it's getting blurred a bit.
Getting blurred out there. If I put it
There
there,
it is.
you can see that. And you can read it free online, artint.info, or just Google David Poole and me and Alan Mackworth, Foundations of Computational Agents. So In fact, a large part of the book's take on agents is um, built around this approach that we've been, this constraint-based agent approach. And yeah, we do obviously focus on the constraints, both static constraints in the CSP fashion and dynamic constraints. So in terms of teaching CP, I mean, I've never actually taught CP, but my theories on teaching AI and constraint satisfaction and so on is that it's important, obviously, to teach, again, combine teaching the theory with the applications. So to see how the applications drive the theory and the theory drive the applications, that kind of mutual reinforcing, I think, is the only way to do it. Either focusing just on the theory or just on the applications is sterile. And the excitement of our field has been the way those have interacted, go back and forth. So what else do I want to say about that? Yeah, I think when you're teaching it, and I learned this, from Dave Waltz's animation, and I did some algorithm animation back in the 70s as well. Visual animations are really powerful teaching tools. For many students, that's the way they grasp these ideas quickly. And so, we developed, with David Poole, we developed AI Space, aispace.org. You can check out various animations of constraint satisfaction algorithms and many other AI algorithms. Students are motivated much more when they can see how it works and they can try the algorithm, they can modify the algorithm, they can try different examples, they can interact, they can slow it down, they can see the individual micro steps or see it at a much broader, higher level. Those things are really useful, and I would encourage people to use them.
So stepping up a little higher again, is there any particular advice you would give to someone starting out in the field of CP right now?
Well, it's the advice I give every AI student as well. Learn the history, and don't just take the history as gospel. Realize that choices were made in history that could have been made differently. See my critique of the development of AI, right? But learn that history. It's really important. People have blood, sweat, and tears has gone into pushing the field forward. And it's worth reading the original papers because often there may be insights there that have been missed by later researchers. There may be nuggets you can pick up, but also just to get into the space, into the mental space of the way people were thinking when they wrote those papers. It's critical. And especially the key papers, trying to say what are the key papers in the area you want to work in and let that guide your search to more key papers, follow that trail. But don't fall in love with a particular approach, often say, this is the way it's going to be, Again, that can put blinkers on, you just see the world through that particular frame, it's a particular hammer that sees everything as a nail. I think, again, it's important to find problems that are challenging for current techniques and see why they're challenging. What could you do about that? And the obvious, most important advice of all is talk to people. Don't hide away and just read papers. Go to conferences, network. Researchers are always keen to talk about their own ideas. They love doing that. So every opportunity you can get, reach out to someone, and you never know what might come out of it. There might be a new collaboration or internship or something. Don't be shy. Put yourself forward and go for it.
Okay. So taking one further step back, what are your thoughts on the current state and the future direction of the field of CP?
Well, I may not be as close to the current state of CP as maybe you are, but from my point of view, it seems like some of the energy has gone out of the theoretical side of CP. But a lot of that energy is going into the applied side, which I think is really exciting. I mean, there's some really important problems. The work that people like Pascal and many others are doing in applications, critical applications in sustainability and energy management, transportation planning. There's so many opportunities for using these techniques for the efficient use of resources and for minimizing our impact on the planet and for, just making the world a better place. I think that's a very satisfying place to work. And it's exciting that our techniques are used to solve some of those problems. And again, as you work on those problems, you'll probably find that the techniques we have aren't quite good enough, or they need to be combined with some other technique, or maybe there's some generalization. So maybe go back to theory. I mean, I know there's a lot of work on, complexity of all these problems and subclasses of problems that have different complexity characteristics. That's important, and it could very well have practical application. But to me, it seems like the energy is more in the applied side, and that's just great.
Okay, well, thank you so much, Alan. This has been great, and I think will be a great resource for the Association for Constraint Programming. And it's just been great talking with you again.
Thanks, Gene, my friend. I really appreciate it. It's an honor, and I appreciate the opportunity.